Hello, thanks for joining me today. I'm Laurence Mailaender, Senior Staff Scientist at Blue Danube Systems. Blue Danube is a startup located in New Providence, New Jersey, USA. Our main product is a low-cost phased array antenna for cellular networks, and it uses specially calibrated antenna elements to uniquely achieve stable directional beams in space. So with that said, let's get into the talk. I will share my screen. So our talk is entitled Receive Diversity Options for a Single Panel 4G-5G Antenna. And my co-authors are Drs. Palat, Nordoza, and Ng, who are also staff members at Blue Danube. So you may be familiar with traditional LTE base station antennas, which are column-shaped and are widely spaced on the top of cell towers. But as we move towards 5G systems, there's a new single panel base station antenna that's becoming the preferred configuration. And these single panels, it's a two-dimensional panel, obviously, and it uses vertical beamforming to increase the capacity of the cellular network, the so-called full dimension MIMO. So it can point a beam both in the horizontal and vertical directions. The question that we're investigating, though, is the potential loss of diversity because we don't have anymore the widely spaced LTE antennas. So the paper is about investigating different single panel received diversity strategies, assuming we have a hybrid beamformer. Now, a hybrid beamformer is a two-stage, analog stage, digital stage beamformer, the advantage of which is it has a reduced number of analog digital converters, ADCs, and RF chains, since we're taking the large number of antennas, reducing it to a smaller number of analog outputs, digitizing them, and then doing the second stage beamforming. So by having a lower number of ADCs and RF chains, we reduce the cost and power consumption. And the investigation, to make it fair, will be based on a fixed size array. The panel, a number of elements on the panel will be fixed, but we're going to change the number of RF chains from 2 to 4 to 8, and to compare that to an all-digital 8R maximum ratio combining. Now, to do the fair test, we also need to have a good spatial channel model that will account for the spatial fading correlation. And we also use dual polarization on every channel. Now, to keep things as simple and clean as possible, we reduce a lot of reality and we just model a single user case with azimuth-only beamforming, flat fading, and no interference. And why do we care about all this? The main question that we want to answer is, can a clever beam design in a hybrid array give performance that's competitive with a fully digital MRC while still substantially reducing cost and power consumption? So this slide shows the different techniques that we're going to be comparing in the paper. And on the left, you see the rows go from 2R to 4R to 8R. So that's increasing complexity. And then we have 4 different techniques that we're calling subarray wide beam, subarray line of sight, pattern diversity, and MRC. So let's look at the subarray wide on the left first. So what you see is there are 4 columns of antennas. So those are the 4 X's. The X denotes the dual polarization. And there are 2 circles, they're wide. So those are the wide shaped beams. And there are 2 of them because it's dual pole. So there's a copole and a cross pole beam, each of which uses the entire array. So in that little graphic, all 4 X's are blue, and there are 2 outputs, copole, crosspole. If we go to 4R, we take the 4 columns and divide them into 2 sets of 2. So now you see blue crosses and yellow crosses, and 2 beams from each copole, crosspole on 2 halves of the array. That becomes 4R. And finally, if we go to 8R, then each beam is simply a single antenna on its own. If we now go to the next column, where we talk about the subarray line of sight case, we now use a narrow beam pattern that is aimed towards the direction of each user. So let's assume that we have some side information that we can form a narrow beam and point it in the physical direction of the line of sight of that user. And like before, we can break up the array into subarrays of consecutive columns. Next, in the pattern diversity case, this case is different because there are no subarrays. So the entire array is used on every beam, and the beams are wide, but point in fixed directions that are determined a priori. So we don't have knowledge of where the user currently is. We just pick a couple of directions to cover the space, and we have a certain number of beams, either 4 or 8. Finally, under maximum ratio combining, we have the sort of LTE case, which is a 4R case. So you see a blue cross and a red cross. So there are 4 outputs: copole, crosspole on the left, copole, crosspole on the right. So that's a 4R case. And there's 10 lambda to get spatial diversity across the 2 columns. And then finally, the optimum MRC solution is the what's shown on the bottom right. So those are the 4 columns, each dual pole, and each one gets its own digitizer and RF chain. So that's an 8R technique. So we want to understand the performance comparison between all of these. Now, about the beam shapes that we're using. I mentioned narrow beam shape and wide beam shape. So on the left, you see those 2 different cases. So if we talk about a narrow beam, of course, the width will depend on the number of elements in each subarray. But here we just used all 4. And you see a beam that's 10 dB beam width is about plus or minus 22 degrees for the narrow case. And there are, of course, some side lobes also. For the wide beam case, for 4 antennas, we use the specific complex weighting shown, W sub BDS, and there are the particular values for it. And that results in this wider beam pattern where you can see sort of 3 distinct humps. But now the 10 dB down point is about plus or minus 60 degrees. And it's also important to notice that the main lobe gain is reduced by about 4 dB. I'll talk briefly about the channel model, but I'll go through this kind of quickly. So we're using a standard TR25.966 channel model, which is sufficient for us. It's a 2D channel model, and it is based on 6 clusters, 6 spatial clusters with 20 subpaths per cluster. It also includes the 3GPP per element pattern. And we simplified this channel model a bit. We only need single cell, 1 user. We don't use any path loss. We achieve flat fading in the model by simply summing all the channel coefficients for the different delays together. We don't have any Doppler. We do have dual polarization, and we only implemented the macro cell type. So here's a little more detail. We don't really need to go into this, but you can now see the clusters and the paths per cluster and the definitions of suburban macro, urban macro. These are the ones we implemented. Urban macro comes in 2 flavors where you can have either 8 degree or 15 degree angle spread. And then we did a little bit of numerical sanity checks on this. So I generate 5,000 instantiations of the flat fading across the array and form a covariance matrix, and then look at the eigenvalues of the covariance matrix. And if we simulate just IID channel values in the simulation, then we get very flat looking components. Okay, let's get into the SNR analysis. This is very important to what we've done in the paper. So what you see here is kind of an equivalent model of a user sending a common signal on 2 polarizations, and it arrives at an antenna array, which has 8 elements, so 4 columns, dual pole, let's say. And we then have an analog beamforming stage followed by a digital beamforming stage. And the digital beamformer is going to be an ideal maximum ratio combining stage. The question is, we want to try different analog beamformers, as I showed on slide number 2, and see what the effect is. So what's nice about this general model is a single model will cover all the cases. So if you have subarrays, for example, then it means you simply insert some zeros into the particular B weighting vector that you want. So let's try to figure out now what is the signal to noise ratio at the output here, given a particular B, which you specify according to whether you want wide or narrow and so forth. So we can look at these beamformer output. Let me start here. So the received signal vector, which we'll break into a copole and a crosspole, is basically the signal from the user comes across a spatial copole and crosspole channel, and we add noise to it. Now, if we take that, let's go to here. So now let's look at the output of an analog beamformer. So we're going to apply beamformer number 1. Here's beamformer number 1 is applied again on the copole part and the crosspole part. And likewise down here, it's beamformer number B. So you see that same thing here with the R expanded into the H-co and H cross and so on. So imagine we have these outputs from the analog beamformer. Now we want a maximum ratio combine those. Well, how do we do that? Well, it means that we take the complex conjugate of each signal part and multiply the received output by it. So for Y1 co, I take Y1 co and multiply it by the conjugate of this term, which is exactly what you see here, and keep doing that all the way down. And if we do that, we'll have signal terms and noise terms. So let's look at first the signal part only. So you just substitute in for what Y1 is, which we know what it is here. And substituting that in, we get some of these terms here. And turning that into a signal power, we basically just will square the whole thing and have the power of S. So that's the signal power that comes out at the MRC. Likewise, for the noise part, we just look at the noise contribution from each one of those terms, follow it through, pretty standard. And we end up getting that the final instantaneous SNR depends on the S term and the N term. The N term depends on this B matrix here, which is the sum of the outer products of all the individual beamformers. So given that, we're ready to look at the results. So in the simulation that we do, we start by selecting either 2R, 4R, or 8R, and we select a channel type, such as the rural macrocell, suburban macrocell. We generate 5,000 channels. We compute the SNR using that model for each specific technique. We then make a CDF of all the SNRs that we get, and we look at the SNR in the lowest 10th percentile. So that's the outage view. And we'll be able to compare the different SNRs, which are kind of like a minimum performance guarantee. So let's start with this simulation output. This is for a 2R case using suburban macrocell channel. And you see the 10% outage is this vertical one. And we have 4 different CDFs. So the poorest performing here is the subarray wide beam. Then comes the subarray line of sight, which gets a little bit of a gain. Then we come to the LTE, and then we get the MRC. So one interesting thing right away is we see that that single panel MRC with 8 antennas actually outperformed the LTE with wide spacing. So that's an important conclusion. And also we see that using the line of sight knowledge and the narrow beam, we are able to gain about 1.5 dB. So that's pretty important. This next slide just repeats for the 2 other channels, and the results are similar. Now let's move on to 4R under the SMA. So this was where we were originally for subarray wide beam. Now you can see subarray wide beam has improved by about 2 dB. But what's really interesting, this is the most important finding in our paper, is that a 4R line of sight case is very competitive, only 1 dB worse than the 8R MRC. So this is really important because the 1 dB gap is small and we have half the number of ADCs. On the other hand, if we do subarrays with the wide spacing, we're all the way back here and we've lost something like 10 dB. Sorry, 5.7 dB gap. So that's clearly not competitive. And then we repeated that for 2 other channels. So to conclude, as expected, from 2R to 4R to 8R, we see performance improvement. 8R, of course, gives the best performance, but needs the most ADCs. Our main finding, 4R subarray with line of sight is indeed competitive with 8R MRC. So there's only about a 1 dB gap. But we do need to know how to point that narrow beam. So perhaps that comes from GPS or something else. On the other hand, 4R subarrays with wide beams is not competitive. Finally, the 4R pattern diversity using the wide beams is equivalent to subarray wide beam. So concludes the talk. Thank you very much for your attention. And we hope you enjoyed it. Thank you.